So obviously what we're going to be doing today is we're going to be calculating with the combined gas law. And I kind of have a couple of rules that we're going to really make sure are satisfied before we kind of choose the combined gas law to do some calculations. First of all, if you haven't watched the kind of more qualitative video that came before this one, I really would, so that you have some sense of what these crazy numbers mean. Otherwise, they're just going to be kind of random algebraic steps. So the first thing we should probably talk about is, what is the combined gas law? Well, if you remember the contributions of all those dead white guys, they eventually came up with this law that had the structure of this, which is P1 V1 over T1 equals P2 V2 T2. All right? Really, all this is telling you is that if I start off with some pressure, volume, and temperature initially, that has to be equal to pressure and volume, the new ones multiplied together, divided by the new temperature. Right? It's not anything more than just algebra. The one thing that I want to make sure that you know is that this is the equation that we're going to be using probably 50% of the time. And the way that we know, or at least one of the many ways of knowing that we have to use this, as opposed to that other equation, which is called the ideal gas equation, which looks like this. All right, we talked about that kind of briefly at the end of the last set of videos. But this is going to be something that we only use if we see moles in the question or grams in the question. And sometimes, like, the only real dangerous thing when you're doing a calculation is that we really have two different equations that we do use regularly. So in general, if you don't see anything about grams or amount or moles or anything like that, we usually are not going to be using the ideal gas equation. By the way, a future video lecture will deal with what we do when we have to do those. So if you're looking for that one and it's a couple of days into the future, take a glance. So we're not going to be talking about this one in this video. We're only going to be talking about this one. So knowing to use this equation is kind of step one, right? The other step that we have to be very careful about is that all of these units, we are going to always convert to one particular unit, right? So let's list those off to begin with, right? So we're going to do pressures, which, by the way, is P. I said it's P. P. These things are always going to be measured in ATM, atmospheres. If you have a question that is not in atmospheres, the very first thing you're going to do is convert that into atmospheres. Our volumes are always going to be in liters. Okay, and that's, the volume of the gas, we're always going to convert to liters no matter what. And then the temperatures, which you hopefully can see, and this is probably the most important one, and also the oddest. These temperatures have to be in Kelvin. If you use degrees Celsius, or if you're a real ruffian and try to use degrees Fahrenheit, this math will not work out, right? So really, the most important thing that we're always going to remember, if your mind is like mine and only able to remember one item of information at a time, turn those temperatures into kelvins if you want any calculation in gas law chemistry to be correct. I should mention that there are questions where usually they involve only pressures and volumes, where it would be okay to stay in some other non-atmosphere or non-liter unit. The problem is that when it counts, you're going to screw it up, because I always did, right? And so the thing that we're going to do, even if, if I turn on the comments here, I'm sure I'd get all kinds of comments about, well, he doesn't need to convert to atmospheres here, right? Well, screw those people, those, fake people that I imagine in my head. I might have a complex, I'm not sure. We're always going to convert to atmospheres, regardless of what the haters say. And really, that's going to be our way of avoiding all the madness. So sometimes it's going to be one extra step that you're not going to be thrilled about. But it's so important that we do that especially when it gets to calculating with the ideal gas equation that we're always going to. So that being said, let's start with your resource guide, which is available on Canvas. I split into two different parts. Part one is going to have everything to do with kind of playing around with this combined gas law. We're going to start pretty simple and then we'll get a little bit more complex. What you'll notice is as long as you keep track of your variables, it's just algebra. With that in mind, a lot of us haven't had algebra in a long time or think we know it and we don't. So what I'm going to do is kind of be real, I don't know, I'm going to really insult your intelligence, especially if, you know, you're really, really good at math. You'll be like, why is he going so slow? I'm just going to make sure that we're all solid in that, and then we'll start to kind of cut out some steps and, you know, once we're good at algebraic manipulation, then I won't make it quite so painful. So let's take a look at that very first question, which will hopefully appear here. As I said, this is all from the resource guide, so just have that on your screen or print it out as it's convenient. Because I have no memory, I put the actual paper over here, so if you look at me like glancing off into La La Land, I've either finally had the stroke that I knew was coming, or there is, you know, a paper down there that I'm looking at. Okay, so the very first thing that we're going to do is we're going to highlight all the different variables that we know at the start of this thing, and then we're going to talk about the variables that we actually have to find. So looking at that question, I see, let's list it off such that we have all of the initial parameters all just written down here, right? And normally when I do word equations, and I'd show you this if you talk to me in office hours, I have like a technique for like underlining certain numbers with units, and then I have like another thing where I put triangles around what was asked. And that's kind of one of those things that helped me out with a little smattering of ADD to kind of concentrate on what all these words mean. But this way, like, this is just another way of looking at things. So initial volume, initial temperature, initial pressure, what we have to remember is no matter what I end up with, I have to make sure that I convert this to liters, that to Kelvin, and that to pressure, right? And the good news is that I can, based on the way the question is worded, I can cancel out some things in the combined gas law to make my life a little bit easier. So I see that 1 liter of gas at standard temperature and pressure is compressed to 473 milliliters. What is the new pressure of the gas? Okay, so I know that I've got initially 1 liter of gas, and I am thrilled because that's already in liters. I don't have to do any kind of conversions. Standard temperature and pressure. Well, standard pressure we talked about, right? And it doesn't tell us anything else. So, you know, let's just use atmospheres, make our lives a little bit easier, right? Standard pressure is that 1.0 atmospheres, right? Also 760 torr, 760 millimeters of mercury, 101.3 kilopascals and 101,300 pascals, right? Or 14.7 pounds per square inch. God, I'm smart. No, not really. I'm reading it. So, what about this thing, right? This standard temperature? Well, it turns out just like we have a kind of a defined standard pressure, we also have a defined standard temperature. It turns out that it doesn't matter necessarily in this equation, but it's probably good to know. It turns out that that is 273 Kelvin, right? How do you know that? Well, because I probably have given it to you somewhere on like a handout or a resource guide or something like that. The helpful thing to remember is that that's 0 degrees Celsius, right? And so scientists just decided we're going to call this the standard that we measure everything else against, right? And it happens to be 0 degrees Celsius. When we start to convert to Kelvin temperatures, if you don't remember how to do that, you'll notice basically all you do is add 273 to all your Celsius temperatures, right? No big deal. So, what is the pressure of the new gas? That is what I'm looking for. right? And so if I was doing my kind of word equation method, I'd put a triangle around that just to kind of remember where I want to go. And so I've got a couple of things that I don't necessarily know, right? I don't know T2. I don't know V1. And back in the day, I used to hate these kinds of questions because like it didn't tell me to keep anything constant. But believe it or not, in this one, it's implied that the temperature is going to remain the same, right? Why? I don't know. That's just the way that these things are worded. So that's what we're gonna assume, and I'll show you what that does to the combined gas law in just a second. Oh, by the way, another way that I knew that that's what you need to do is that this is a Boyle's law type question where temperature is kept constant, right? It even says Boyle's law at the top, so, you know, it's kind of a pain in the butt. But what we're gonna do is we're just gonna kind of cross this off, and I'll show you why I'm doing that in terms of using the combined gas law. We're just gonna assume that this is constant, right? I could have written 273K out there, but that just kind of confuses me. So let's actually write down the combined gas law and then figure out exactly what we're gonna do. Oh, whoops, I forgot to put the ending volume, right? And so I should put a 2 here also. Holy crap. Okay, so it actually does give me a second volume when I'm looking at that thing. It's 473 milliliters. But just to kind of conserve board space here, I'm going to convert that into liters in my head. Let's hope that I do it right. I've got 470.473 liters, right? So milliliters, you divide by 1,000. You could do that in a dimensional analysis, but I don't want this video to go on, you know, more than it has to. So I just kind of did that in my head. A little dangerous, but we'll go with it for now. So now let's take a look at that combined gas law. Right, we've got P1 V1 over T1 equals P2 V2 over T2. But the good news is I crossed out those two temperatures because it's held constant, right? So I could, of course, plug 273 in for both of these, but that just makes the math a little bit more complicated, right? The good news is if this is the same, we're just going to cross those out, right? We're just going to assume that they're one. That's the beauty of using the combined gas law, is that if you know what is held constant, you can just cross it off, and then what you end up with is whatever dead white guy's law you happen to be talking about. Here it's Boyle's law. Could have just as easily been Gay-Lussac or Charles's law if you watched that last video. Okay, so once we get to this point, one of the things that I like to do in anytime I'm doing like a physics calculation or a chemistry calculation, I don't like to plug numbers in until I'm ready, right? Like I like to solve for the variable first because it requires me to write less, and I'm an inherently lazy human being. So what I'll do is I'll say, okay, well, what am I looking for here? Well, I know that I need to figure out a new pressure. And what I'll do is I will rearrange this thing using algebra to get P2 alone, right? And what I'll probably do is I'll erase a little bit of this and kind of maybe redraw it in a slightly different way to keep things clean. All right, so let's do some algebra based on this little sucker right here. First thing I'm going to do is make my life a little easier just to organize things in my brain. And these things I'm going to get rid of completely, and I'm going to redraw it. So what I end up with is Boyle's law, which is P1 V1 equals P2 V2. What I need to do is I need to solve for whatever's in that box. And one of the beauties of algebra is there are operations, which you'll hopefully remember, that reverse the effects of any operation mathematically, right? So here you'll remember that these guys are an indirect relationship, right? So it's a multiplication, right? So that means that this side, which is also a multiplication, means that I have to do the opposite. And what I'm going to do is I'm going to divide by V2 on both sides in order to get P2 alone. And then I'll redraw it. So let's do this in red. Anything kind of mathematical that I'm doing here, I'll do in red. So I'm going to divide both sides by V2. And then when I redraw this sucker, let's do this actually. The reason I did that is to get V2 to go away, right? V2 divided by V2 is just 1, so that goes away. And what I end up with is P2 equals P1 V1 over V2, right? So this is really the new expression of the combined gas law based on my question. Once I've gotten to this point, really all I have to do is do the old plug and chug, right? And so hopefully I'll put like a screen capture of all the values that we wrote down in the first part of this video here. And so my first pressure was 1 atmosphere. My volume, I've already forgotten, but I think it was 1 liter. I am going to divide that by our new liters, which is 0.473 liters. And one of the kind of oddball things you've noticed that I've done here is that I've included units. You don't necessarily have to include units, but I like to keep track of them to make sure that things cancel out when they're supposed to cancel out. And so, for instance, I can tell that I want to solve for a pressure, right? So I should be left with atmospheres in terms of units. So it turns out that the liters over the liter will actually cancel out such that it just leaves me with the units of atmospheres. That's really just kind of something I do to keep track of units, make sure my calculations are okay. If that confuses you and makes things difficult, just use the numbers, right? Just plug in the numbers, that's no big deal. Okay, so let's see what we end up with for our calculation now. Well, my calculator popped out 2.114 atmospheres. By the way, I used 1.0 back at the beginning. I probably should have done 1.00 in terms of sig figs, but if you don't care about sig figs, the heck with it. That would have given me a little bit more of a precise answer. Doesn't really matter because hopefully this number still makes sense to everybody. 2.1 atmospheres. Answer to the question, QED, bam, we're champions. What I always do at the end, which you're going to be really sick of hearing, is I sniff that answer to see if it really makes sense, right? So keep in mind that pressure and volume are inversely proportional, and I know this is painful, but stick with me here, right? So what I did is I lowered the volume, right? I basically halved the volume, right? 473 milliliters is just about half of 1,000, right? Which is what I started as. So my pressure should have doubled, right? Because it's an inverse relationship, right? Lower the volume, I should have increased the pressure. And in fact, it did, right? It went from 1 to 2 approximately, right? And so that's what I mean about sniffing an answer. Let's try another one where we have to do a temperature conversion, which is the second one on your worksheet here. And then maybe we'll either go through a couple of the combined gas law problems, maybe at least one, and maybe like one from the homework just to kind of keep you guys watching. Okay, so our next question should appear right there. And we're going to go through and keep track of all those variables. And if there's anything that is kept constant, we'll cross it off just like we did before. Okay, so I tried to keep track of everything that was given to me in that equation. One of the things you'll notice is that there is no mention of pressure, but if you kind of think about the, the question, chances are that if you have a refrigerator, right, that thing is going to be at a constant pressure. Most of us don't have a refrigerator that's inside of like a vapor lock or anything like that. So we're going to just assume that this is, let's say atmospheric, 1 atmosphere. It actually doesn't matter because it's the same. So we're going to do that same kind of deal with pressure. And just since that's constant, we're going to get rid of that. And so what we've ended up with is this thing that involves temperatures and volumes, which is in fact Charles's law, but a big but, right? We've got temperature in Celsius. Blah! Right? That is never good. We do not want temperatures in Celsius. We're going to convert each one of these to Kelvin. We're going to add 273 to each one of these numbers. I don't really have much space, but yeah, let's just write it down like this, right? So we're going to do a plus 273 and a plus 273. And for this guy, if I can do this complex math in my head, that's 295K, and this one is 277K. And now we are ready to take that combined gas law and simplify it a little bit. There's a combined gas law. Let's keep in mind what we're solving for. So we are solving for V2 right here. And what did we decide was constant? The pressure is constant. So let's do this. Get rid of those pressures. And so what we end up with at this point is V1 over T1 equals V2 over T2, which is just Charles's law. Remember that we're solving for V2. Just like before, algebraically, I like to do all the algebra with just the variables, and this is something like I say, you do a lot in physics and chemistry. If you want to plug in the numbers, go for it. But what we have here is a division, so the way that I get rid of a division is a multiplication. So I'm going to take both sides and multiply that by T2. By doing that, this guy goes away, and what I've left with is a new manifestation. Oops. A new manifestation of the combined gas law, which is V2 equals T2 times V1 over T1. There we go. We got a plug and chug. I'll put all the numbers in here and we'll see how it works out. I've got everything plugged in right there. We are going to keep track of the units just to make sure that our volume really does end up with liters. And our kelvins are going to cancel out pretty nicely. And let's see what the calculator shows us. So there's the answer my calculator popped out. One of the obnoxious things that people are sometimes angry about, which is also a reason why we really like precision in science. After you've finished this calculation, what you'll notice is that the volume has really not changed, right? In a sig fig sense. And that actually, believe it or not, sniffs right? Because if you're going to put something in a normal refrigerator, right? It's not that different in terms of that absolute value of temperature in Kelvin, right? And so the volume is not going to change that much. It did, it went down a little bit. But the only way that you'd get like a real observable volume change for something like this is if you use something that was incredibly cold like liquid nitrogen, or I guess alternatively started with something really, really hot. So believe it or not, even though this is the same number we got that we initially had, it all sniffs right and all the math seems to be working. So let's try one of the combined gas law problems, and I'll try to choose one that has kind of a tricky algebraic step that you have to watch out for. Okay, I lied a little bit. I thought it might be a little too quick to just jump right into kind of the most difficult algebraic manipulation and type of gas law question. So what we'll do instead is we'll do number 13 on the homework, which is in fact a combined gas law type question. We'll go through that and then we'll jump into that slightly harder one, which is also on your homework. Okay, so somewhere here we hopefully will be able to see the question that's being asked about that balloon that went way up in the upper atmosphere. Incidentally, these are real calculations that you might have to do if you're like a meteorologist or something like that. Certainly scuba diving, things like that is another place where keeping track of these kinds of bits of information is important. But anyway, I recorded all the different units with numbers that were given to us, and then I also, as always, put a circle or a triangle or a box around whatever we're looking for. So a couple of things as my eyeballs look through this. I want to make sure that everything's in the correct units. So the volume is in the correct unit. Temperature, of course, is in Celsius. We're going to have to convert that into Kelvin. That pressure is an atmosphere, is all is good. Another temperature we got to convert to Kelvin. And then the truly obnoxious thing is this appearance of torr, so I'll show you how to convert those guys as well. So again, every single unit conversion we could do in a dimensional analysis, like this guy right here. But what we're going to just kind of learn to do is divide by 760. If that, makes you crazy, I apologize, but it's just like a really quick way to take millimeters of mercury and to very quickly convert it. So I'll do that in a calculator in just a second. Obviously, all of these temperatures, we're going to have to add 273. And that'll give us our new Kelvin temperature. So I'll do all those calculations and then we'll take a look at what we have to do algebraically. Okay, so make sure you check my numbers. The only thing that I wanted to mention something quick about is this rat's fart of pressure right here. You'll notice that I only used 2 sig figs, but if it's not like the final reported value in terms of significant figures, keep in mind it's usually a good idea to keep a couple of extra non-significants that you can then round later. If you're really into that thing, who cares, sig figs, let's just get this thing right to begin with. So, just like always, we're going to go ahead and write out that combined gas law. And what we need to do is rearrange this thing so that we are solving for the correct quantity. And as always, we're going to put the box around V2. And then we'll solve for that. So we're going to do a couple of steps at once here algebraically. So we're trying to solve for the final volume. So we are going to multiply both sides by the reciprocal of this. Right? It's kind of like doing a multiplication and division all at once. Hopefully this doesn't terrify anybody. We'll just do it in this color. All right, and so whatever I do to one side algebraically, I have to do to the other side. And what I'll end up doing is, let's do this one in red. T2s will cancel out, P2s cancel out, and what I end up with, if I rewrite it and then kind of switch it around, is the fact that V2 is going to be T2 times P1 times V1 all over P2 times T1. So hopefully I wrote everything correctly there. I'll fill in all the numbers. We'll keep track of the units, make sure everything cancels out, and then hopefully we'll have our answer. All right, hopefully you can read that gobbledygook. So assuming I've done everything correctly, we should end up with liters as our units for our answer. So make sure that that is true. The K cancels out with the K. ATM cancels out with ATM. And in fact, we're left with those units. And all that remains is to plug this correctly into my calculator, which I rarely do correctly. Okay, there's my answer. You'll notice that I don't have too many sig figs, so what I should do is round this thing properly. So if I were to round that sucker properly, in terms of sig figs, 1, 2, 3, 4, 5, 6, this is what the answer would be. Right, 240,000 liters. A lot of people don't like losing all those numbers, and some people like to use scientific notation. So what we can also do is round this thing as 2.4 times 10 to the 5th liters. Both of those are completely acceptable answers. As I said, if you're a hater of sig figs and they really confuse you, ask me about them. Good news, like on let's say this was a 10-point question, sig figs for us would never be more than like a 1 or 2 point kind of thing. I'm much more interested in you being able to calculate things properly. And so here it is. So let's try one more that's pretty much as bad as it can get in terms of doing algebra and calculating with the combined gas law. All right, last question on the homework should appear somewhere around here. I've written down all the important values. One thing that you'll notice is that this is kind of, I don't know, worded backwards if you pay attention to the words. Like we're given all the final values and then it's asking about the what the initial values started as. Doesn't really matter as long as you kind of keep all those items of information together. So in other words, like what you call the ones better all stay with the ones. What you call the twos better all stay with the twos. Blah 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 blah. What we're going to be doing now, one thing that the reason I included this is that this is like the trickiest thing to do is to handle temperatures. If you remember back to the combined gas law, temperature is always in the denominator, right? And so what happens is algebraically sometimes that screws students up. So I'm going to show you a fail-safe method that you'll never be tricked by one of these kind of like chances where you might be actually accidentally solving for 1 over t instead of what you want, which is t. Another thing that's a real pain in the butt, I almost said it, a real pain in the butt about this is that we notice that everything is given in terms of degrees Celsius. Not only that, they want the answer in degrees Celsius. The problem is that we need to go to Kelvin. So really what we're going to have to do is we're going to have to take that thing, convert it into Kelvin so that we can solve for a Kelvin that we then convert back into degrees Celsius. These combined gas law questions that involve temperatures are usually, or an unknown second temperature are usually the toughest. So let's see how to attack it. First thing we're going to do, as always, go through our units, make sure we've converted into everything that we need. Nothing we need to do there. That pressure looks good, that volume looks good, that temperature we're going to have to convert. We're going to add 273 to that sucker. And so we're going to end up with 298 Kelvin. And now we can start with that ideal gas. Now we can start with the combined gas law. P1 V1 over T1 equals P2 V2 over T2. And so what we are going to do is after I take a snapshot of this so that I can include it in the corner of the screen, is we're going to see how to manipulate this to actually get T1 alone properly. First thing we're going to have to recognize is that when we cross multiply, we can set two sides equal to one another, right? And so what I am going to do, as I said, I'm going to try to keep red as being kind of like the algebraic manipulation color. And what we're going to do is we're going to cross multiply T1 times this, and then also T2 times that quantity. And I'll write that sucker up there. Once we've done that, you'll discover that it's pretty easy to solve. If you do anything else, I'm not saying that's the only way to solve this thing, but just be confident in your algebra and check your answer before you come to an exam or something like that. This is the method that I almost exclusively use anytime there's some sort of ratio like this. Okay, so let's solve for T1. Now it's just as simple as dividing both sides by P2 V2 in order to cancel it out. So we go P2 V2, and then we do the same thing to both sides like we always have to do. When we do that, it automatically makes the pressures disappear, the second pressure disappear, and also the second volumes. And lo and behold, we end up with the equation that we're going to use, the reimagined combined gas law equation that'll allow us to solve the problem. Stick with me, we're almost done. Notice that I've written the units up here, and this is always my check to make sure that we are going to end up with the right units, which should be in Kelvin. So my atmospheres cancel, my liters cancel, and I'm left with Kelvin just like I want it to be. But you'll keep in mind that the answer has to be in degrees Celsius because some jerk made it that way. Assuming I did everything right. There's our Kelvin temperature. Okay, and keep in mind this is in a freezer, so it should be pretty cold. So it looks pretty cold to me. But what we're going to do to convert this Kelvin into Celsius is to subtract 273, just like we added 273 before. And what we end up with is, I've got minus 33.88 degrees Celsius. Of course, now we're ready to report our answer, so we're going to round to the right number of sig figs, which is minus 34 degrees Celsius. So thank you for bearing with me through all this calculation. I know it's painful to watch calculations online. I don't know, it could be better or worse than being in class watching somebody type on a calculator. So on the next video lecture set, we're going to be talking about using the ideal gas law. We're going to build in to doing stoichiometry again and mole conversions with gas laws. Yay!